And this is our cars. Here is the content that we are gonna present. Well, first the goals of the project, the design of the grabbing system, electrical connections, control algorithm, communication, and conclusions. We don't have much about the visual part because of the issue that we said before, that our colleagues are not even managed to do that much, but we try to present the rest. Well, first the goal mainly was to create a car that would manage to grab a ball by detecting it with artificial vision algorithms, and then shoot it towards a goal. We had some extra features that we wanted to implement, but because the time was not that much, we didn't do it in the end. If I'm right, we thought at the beginning of rotating the camera only with a servo motor, and then also implement some kind of energy saving modes to keep the power low. Well, in the first couple of weeks we were designing the grabbing system. I thought of many designs. This was the first one. I designed everything but these parts that I downloaded them from GrabCAD. We decided not to go for this one because we thought that maybe it was not gonna be so robust, even though that the bucket can be made as big as possible, but that also increases the weight and everything, so we decided to not go for that. This one was thought because we saw some mechanisms on the internet, on YouTube, of other robots grabbing balls, and this one was kind of quite popular. Usually not like the flaps like this, but only with kind of like wires or something that were grabbing the balls. And then at the end, well, this one would have also like some pitching wheels in here that would shoot the ball quite fast. And in the end, we tried to merge this with an horizontal version that would be, that one is the actual one. At first, we also thought of putting the pitching wheels in here, so the shooting would be faster. But yeah, we decided to go first for a simple version that could work just by pushing the ball. We tested it, it worked quite well. The balls were going quite straight, even though it was not real conditions because the robot was not moving. It was just the ball being close to the mechanism, and that was it. Well, this one is working with two servo motors that are placed in here. This was also for simplicity, kind of, because sometimes it's easy to program a bit more and not to struggle with mechanical mechanisms. But indeed it would be better to just have one motor in the middle, for example, and here a couple of springs, and that could give even more power probably to the shooting part. In here the design parts, well, I designed also everything but the servo motors that I also got them from GrabCAD, and in here they are not, well, yeah, in here they are already kind of designed for being printable, because at first we made some versions without thinking on the printability of the parts, but then we adjusted them just to for example, cut this part in 3 sections and stuff like that, so everything would fit and would be printable. Well, this is also the assembly of the car that we made to make sure that everything was gonna fit correctly. Then in the electrical connections, we made a couple of changes. Basically, we stick to the guide, but for example, we realized that the pins, well, this is moved, should be here, that the PWM pins that were chosen were working at different frequencies according to the Arduino website. One of them was working at 460 or something like that hertz, the other one are at 900. For some reason that was generating like for full voltage or no voltage it was okay, but in voltages in between it was not generating the same desired voltage for both motors. So we decided to move this cable to pin 6. Well, we used 5 and 6. Right now I cannot see which one is which one, but we use 5 and 6 that both work at 900 hertz. Then by measuring, we just measure with a multimeter, which is not ideal, but that filters the voltage indeed. And we saw that in that case the voltage for each PWM value was the same. Well, then in addition the I2C communication was added. Then the actuators were decided to be connected to the Raspberry Pi because we had the PWM in there, and it was kind of easy to split. In addition, because basically the main control comes from the Raspberry, it's quite easy to detect already a ball really close in the visual algorithm and send from the Raspberry the command close or open to the motors without going through the Arduino. That doesn't make that much sense. We use the PWM pins, this one and this one, and that was it. Then in the control part, I decided, well, at first we implemented only a position control. It was working, but there was a bit of overshoot, and then after some research I decided to try to implement a second loop in cascade to control the speed. I had a meeting with Dragan. He told me that probably this was not really needed, because actually you are controlling already the position, and the speed should be controlled kind of already. But actually the results that we got from this were softer, and we decided to keep it. He also explained me that probably the best solution would be to implement like a feed-forward gain at the beginning, and that would take most of the charge of most of the computation part of the control, and it would be better. He also asked me to, well, if I have time, to send him some the response of the motors with some noise that as an input, and he would give me the ideal coefficients for K, P, and D. But I didn't have time in the end to do that, and because it was working already, I prefer to continue working on other stuff. This was the response. These graphs, I got them yesterday because the battery was low. It didn't reach the maximum threshold that we had for the speed. But yeah, it can be seen. In here we were giving a command of 10,000 pulses to both motors. As it can be seen, they don't follow each other perfectly, but the deviation is not that much, and we also tested it before that because in the end this position control is gonna be in the same orientation as we wanted. In the end it's gonna correct even if one is a bit ahead to the other. Also, these final peaks in here are not desirable in speed, but we didn't think of how to adjust that. Also, the parameters were tried to be adjusted with Ziegler-Nichols system. We actually did it, but the result was not that good. So we just did some empirical adjustment by first adjusting the p value, then adjusting the I value, and then finally the d, which is quite low. Yeah, then the communication is using I2C. The Raspberry Pi is the master because it's working at 3.3 volts, so the Arduino can detect that as a 1, but the Raspberry Pi would burn at some point by using 5, that is what Arduino uses. It has internal pull-ups, so we didn't have to add more. And yeah, that was it. We didn't go that much into the speed of the pass. We didn't adjust anything, just the default values from the libraries, because we thought that it was enough. We tested it. It was yeah, it worked, and that was it. We didn't implement actually the current sensors. We didn't try to read them, but they are also connected in there, so it would be just a matter of software to adjust the read.
Yeah. Okay, so just to reiterate the grabbing and launching mechanism, so we decided finally to do this this final design that was initially designed by Ricardino and also designed in SolidWorks by him. So we printed it out, had several iterations, and again we have demonstrated the working of this particular one in one of the halfway presentations, so we know it's reliably working. Rather surprising as well, because this particular design, while it might seem simple, we didn't find any existing variant of this particular design with just a simple, almost like a door open and close hinging mechanism. We didn't see this in any sort of because this kind of situation is most common in battle bots and sort of competitive ball catching robots or whatever, but we didn't see this particular mechanism, but it worked surprisingly well. The actual pitching ability is somewhat impaired, but for a distance of 1 meter, we think that even in a practical setting, while not tested, would be perfectly fine. And also the accuracy was a main concern, but as long as the 2 parts remain rigid and don't get caught in the bolts, it's actually surprisingly accurate. It's very straightforward. And moving on to the visual part, well, first on the driving. So the control system that Ricardino just explained works very well. So we are able to achieve all of the necessary requirements to complete the requirement of the course, the objective. So all of the sharp turns are done quite precisely. So the control algorithm has been probably working. We have videos and documentation to back that up. And of course, commands given from the Raspberry Pi to the Arduino. So for the visual part, I will roughly try to summarize what my teammates have done, since they are not here today. So I think the biggest thing to talk about in this change is that simply for the camera placement, we didn't stick with it all the way down here. We did raise the camera higher so it is not obstructed, since we had a rather large mechanism in front, which may have obstructed vision. So we raised everything up slightly on one of the camera mounts that are provided on the on-course side. And we attached the camera on there, we fastened it over there. So the goal detection, there will be images in the next slide. So detection, essentially we applied the HSV mask over everything to detect the color, and then we did contour detection plus we also did the template matching to ensure that we figure out exactly what the goals are. So we made use of those 3 individual squares on the goals and be able to detect them. So while the robustness is an issue, I can show you quickly how this looks in a practical setting taken with the Pi camera. So essentially what happens is we evaluate the raw image, we get those using the HSV mask, and then evaluate that using the contour and template matching, and the final result seen by the Pi is this, or seen by the entire robot is this. So this is done outside, of course. So again, for certain images it was fine, but overall, as per the information provided to me, in all of the testing it wasn't nearly as robust as we would expect, but indeed it was successfully implemented, as you see over here. So ultimately, we do get to have that contour detected at the end of it. So based on that contour is what's going to form the foundation of our path planning later on. But moving forward with the ball detection, unfortunately, Thomas, who's our 3rd member in charge of ball detection, was not responding. But I did use some of his presented information in the last few mid-presentations about the ball detection using an HSV mask. And eventually we were able to successfully, at least from still imagery, extract the contour for the balls quite successfully and apparently allegedly robustly. So the path planning, I think most groups have a very simplified approach to path planning, and our group is no different. So the algorithm that was intended to be used, and this is actually the only part that we don't have documented, since we don't have a working model at this particular instant of time. But the idea is very simple, which is simply to find out the center of our detected objects, the detected objects being the balls and the goals, find the center, and then evaluate distance of the pixel in the center to the center of the screen, and then simply turn left or right, depending on whether or not the object is to the left or right. So that's the very, very simple, very basic idea, no advancement done over there. In terms of brief idea towards extensions, as Ricardino did explain, we initially planned to rotate the camera and then to do some power management. Also, some initial exploration was done to the neural networks, but that turned out to be, if anybody did try that, if you didn't try that, good for you, because that was a major waste of time, but that was also implemented. But in isolation, every part except for the path planning has been demonstrated and documented. At one point, I think, wrote the course, but we are unsuccessful to be able to be presenting the final one, as explained earlier. But those are the parts of the presentation. So that's all we have for today.
You have some questions, Martin?